analysis of big data. And big data analysis in that space means taking diverse data sets that have extremely diverse schemas, large volumes, large velocities, and trying to build lots and lots of applications on top. So to give you an example of the types of application you might build, in the cybersecurity realm, some of our adversaries would be able to adapt very quickly to some of the techniques we use to discover what they're up to. So if we're trying to protect U.S. critical systems, our adversaries might figure out in a week or two that we're onto them, and they might change their tactics. So we'd have to build another application to figure out what they're doing, how they've changed their behavior at that point. So this game of application building is essentially who can evolve faster, and we evolve faster than our adversaries in space. And I see a lot of parallels to business strategies in that case. Finance industry, healthcare industry, health and similar industries. Building an application is essentially a way of taking innovation and putting it into a package that's then reusable, perhaps in a workflow, complicated workflow, with lots of other different applications. So some of the challenges associated with building applications are figuring out what schema is of all this big data, where we get a new data set in and we're going to build a new application to adapt to the new data sets, but kind of automatically take advantage of all the data that's in there. Multi-level security was a huge problem in my previous space. So that was, I have data sets that are protected by different requirements, people have different roles, and it's a complicated set of roles that's required to see portions of the overall data set. So we have those types of multi-level security problems. There's a few ways to attack them, right? One is build it into the application space, which the more complicated the data sets, the more complicated the security requirements, the more expensive it is to build applications, and that doesn't help us evolve very quickly. Right? So we were looking for a way of really encoding a lot of this data-centric security, multi-level security problem into the infrastructure space. We build applications more quickly on top of it. So outside of the intelligence community space, multi-level security is required when you have data that's protected by legal restrictions or protected by privacy policies. So probably everybody in the audience deals with some data that has some type of privacy restriction on it. If you don't, you probably should, because it would be great to bring that in and enhance your applications, I would imagine. Okay, so that's 4 motivations there. All right, so 4 things we're trying to do with this Accumulo project: cell security, scalability, so be able to reach in a single data center tens of petabytes plus. Diverse interactive analytics, so things that have sort of low latency or real-time fields in them. And flexible adaptive schemas. So the concept there is to be able to bring in a new data set very quickly before you understand the schema of it, be able to run discovery analytics on top of it, so you can then understand the schema a little bit better and refine it as you go. So we built Accumulo. At its core, Accumulo is based off of Google's Bigtable model. So it's similar to databases like HBase, for example. And we've added a little bit of innovation as we went. Okay, so here's how this works. How many people use HBase? How many people use Accumulo already? All right, so I got some work to do here. That's good. Accumulo is a key value store. It stores key values in sorted order. So keys are 5 tuples that consist of a row portion, a column family, a column qualifier, visibility, and a timestamp. And those are all sorted hierarchically, so row first, then column family, and so on. And lexicographically, right? So they're byte arrays, and they're all sorted lexicographic. This key is very similar to the age-based key. One of the main distinguishing features here is we've added a visibility label to the key itself. So the visibility label, it has a language associated with it, which is Boolean logic, and it allows you to express at this fine-grained key value layer how that data can be shared. Okay, so we'll use that as we go forward. So in particular, here's the syntax and semantics associated with that document label. If I have a user come in and query, that user comes in with a set of authorizations. So here we've got two users represented in the upper right, Captain Kirk and Mr. Spock. Captain Kirk is Federation human, while Mr. Spock has the additional role of being Vulcan. Right? So if I have a set of documents and various protections on them as to who can see them or what roles are required to see them, document 2 can be seen by, for example, either Klingon or Vulcan, and document 3 can be seen by only someone who's Federation human and Vulcan. Right? So it's a silly example, but it translates pretty naturally into restrictions that are placed in law or in privacy policies. Okay, so stored key value pair is that core data element inside of Accumulo. In order to distribute this and scale up, I need to be able to partition it and do some kind of a divide and conquer approach. So we're seeing a diagram of tables on the bottom here. So there are key spaces, there are 3 individual key spaces, each of which is globally sorted on all the keys. And then on top of them, I have this 3-level hierarchy in that data, which is essentially, I can go to this well-known location, Zookeeper, find the root tablet, from there find the metadata tablet that holds information about the data tablet that I'm interested in. I've got 3-level traversal to get the data that I'm interested in, and each of these tablets, these portions of the tables, can be split up and hosted somewhere in the cluster. So it's a unit of work that's distributable across my tablet servers. All right, so from a process level diagram, this is what we have. On the right, we have applications that are talking directly with tablet servers. Tablet servers are hosting tablets, right? There's portions of tables. And then there's some background operations that are responsible for managing the tablets, the distribution of tablets across the cluster, and making sure that they're all hosted at any one point in time. Accumulo backends this data in HDFS, and it uses Zookeeper as sort of this distributed blocking authority. So this application space could be MapReduce processes, could be web services. It's a very diverse set of applications that are supported there. Inside the tablet, I'm concerned with 2 different operations. So once I've already figured out which tablet server is hosting that portion of the data that I'm interested in, I need to either read or write keys to it. So writes come in random order as mutations to a row. So it's an atomic change in some number of columns in a row. And reads come out on the other side as a sorted sequence of key value pairs in a range. In between this sorting operation takes place. And this uses a log structure merge tree, just like Bigtable, just like HBase. So keys come in and they get put into a balanced binary tree, this inner map. At the same time, they get put into a write-ahead log, which is used for recovery, but it's a sequential write to disk. Eventually, the in-memory map fills up, and a background operation does an action, which is another sequential write to disk, writing a sorted file. Several sorted files get written. Eventually, we want to merge those files together, so we read them and we sequentially write them to disk. So this essentially turns random writes into sequential writes on disk through a series of background processes. And disks are faster when they're sequential, so it's a good thing. On the read scope here, we are trying to stream a series of key value pairs out So we have to read from any of the active files and remember that as string those keys to whatever client is interested in reading them. So also in this diagram, we have something called the iterator tree. Right? So as I'm compacting, as I'm taking my in-memory map and dumping it into a file, this is a natural place where I'm streaming key value pairs and sorted order through the processor. I can do other types of operations in that space. Right? So it might be like a filtering operation, it might be an aggregation operation, all sorts of applicational operations can take place in that space. And that actually allows us to turn writes that otherwise would have been remodified write into kind of transform it lazily through this write structure. So it gives us good performance for doing aggregation. Okay, so that's essentially the core technology of Accumulo. On top of that, we have now an API that supports using rights to key value pairs and ranges of key value pairs. But that's kind of a long way away from building an application on top of it. So in order to make sense of that, we need several techniques or design patterns in this space. So that's what I'm going to talk about now. So let me introduce this hierarchical decomposition diagram. In a SQL database, you have a data definition language that defines what are all columns in the table and how are they indexed. We don't really have that in a table, in a flexible schema table, where at any time we can write new columns. You can change the schema by just writing some value pairs. What we can do is sort of group things into hierarchies and make sense of it that way. So when I query Accumulo, I query for a range, and that actually translates into a prefix in the space. So I can define a range that's everything in a row or everything in rows that start with some sequence of characters or row and column family. But it basically starts at the top and goes down to some specification level and then scan over everything that's below it. So here we've got an example of a table that is focused on people, or entity focused. So at the top we have person. We group all of the keys into attributes or purchases or returns within all associated with that particular person, and then so on and so forth going down this hierarchy. So person here is just fill in the blank. When we actually instantiate that, it's like this. Here's a complete table for Bill and George and some attributes and purchases for them. So we selected here a traversal from the root to the leaf in this diagram, and that becomes a key value pair. So any traversal from the root to the leaf, Bill's 40% there, that's a key value pair in the system. So this hierarchical diagram lets us define what key value pairs can exist. Okay, so I'm just going to use this as a tool to describe the basic design patterns that we use on top of it. So here's the core one, right? This is forward index and inverted index. Basically, all of the design patterns that we use are derivatives of this one. Essentially, if we're focused on events, then might have a unique identifier, a UID perhaps, and then within that is going to be some combination of fields and terms. Right, so if I have a forward index and I know what I'm looking for, I can define a prefix in there and say, give me everything that's in a particular UID and get a bunch of field term combinations. If I wanted to query that and say, what are all the events that have a particular term in a particular field, then I need an index, right, a secondary index on that, and that's the inverted index. So here's basically two different tables, forward index and reverse index table. So the inverted index takes terms, you can search on the prefix that has terms, and get back a list of UIDs. So from another perspective, this is what that looks like. If I take a single event, I can map that to one place in the event table and several places in the inverted index. And then if I have a term that I'm querying on, I can find that as one continuous range of key value pairs in the inverted index and map back to multiple places in the event table. So this type of indexing differs significantly from standard relational database my fields all get thrown into the same index. Okay? I don't have an index on a particular set of fields, I just have an index on all the terms. So that's useful for a couple of reasons. One is if I don't build my schemas ahead of time, it still gives me a way to query across all my data. And two is I can use it to do some types of pre-joins, you might call them. So if I want to say, give me all the data where this field equals this field, the entries that have that. I can basically just scan all the terms and do a cross product inside of that local space, and it becomes a scan and then we process it. So I'm not going to go deeper into that. Okay, another design pattern is graph processing. So we want to do graph analysis where we have arbitrary entities, just abstract entities, and relationships between the entities. So those relationships can be a number of types, but they all fit into this data structure, which is a graph, right? So we're focused on a node. From a node, we query all of the edges, the out edges, the in edges, the node info. Forms a graph. You do self-joins in that. You do input expansions, frontier expansions, and that becomes a primitive that you can use to do all sorts of graph operations. You can also do multidimensional indexing, so geographical indexes, for example. This is a space-bound curve technique. So here we're taking latitude, longitude, and depth, and interleaving them to form a geohash, and using that geohash as the row in the index. And that has the property of defining ranges or squares or cubes inside of this multi-dimensional space, and that translates to a small number of ranges inside of our one-dimensional keys over. So it's an efficient way of doing proximity queries or box type queries. In addition to that, one thing I didn't mention earlier is that Accumulo partitions its keys based on row boundaries. Okay? That means that all of the keys that share the same row identifier get put into the same tablet and are hosted on the same tablet server and are therefore in scope for the iterator tree that I mentioned. Okay, so if I wanted to do a server-side operation like some type of grouping, if I can do that within that partition space, then I can write it in iterators. And this is what I get a document partition type indexing. So this is a shard table. What I can do is take all my UUIDs and partition them into subpartitions. And then within that partition, I can put all of the index entries and the document entries for those documents. Right, so that gives me the ability to do really like Lucene type queries very efficiently without having hotspots that you might get from a term distributed index. Alright, so here's another view of that. Take my event, I stick it into one row, but a different set of columns. So one of the points I want to make of this is that if you don't have a fixed set of columns in every row, you can really scale up to possibly hundreds of millions of columns. Right? And we do that. We have rows that have hundreds of millions of columns in them to do this type of indexing. And it's a very efficient way of having generic discovery analytics. Okay, so this scales to doing things like inside of the iterator tree, I can represent Boolean logic queries. So here I've got on the right a graphical representation of the iterator tree for foo and borrow fast. So I can take index portions of that row, merge them together in a sort of merge operation, look up the documents that they refer to, and pass that back. All that operation happens on the server side of the client, and just get the results that they're interested in with a much richer query language. Okay, so those are essentially the techniques that we use, the core techniques that we use. On top of that, we really want to expose expose these at a higher level API. And this is future work for Accumulo. It's actually work that sqrrl was doing to build our product. So, Q-value pairs are great. You can do all sorts of cool things with Q-value pair, but it can be challenging, right? You have to understand a lot about Hadoop databases, how to do indexing in databases. And it would be great if this were exposed in higher level APIs, right? So we're trying to look at what are the right APIs to expose these things to. I think we've seen query language is great. A lot of people understand that. Gives you kind of that Google search bar type of query capability. That's universal search. Lots of people speak SQL, especially when you're doing like stats processing, like OLAP views. SQL is a very natural language for that. So we're looking at supporting that inside of the sqrrl product. Okay, so once you get that higher level API exposed, the idea is you can do very quickly build these applications that do interesting things like combine information retrieval and graph search to do a simple visualization. So this is a little demo we're throwing together here. I'm not going to do it live today, but it's sort of candid. So I've done a query for Abraham Lincoln, and that pulls back a bunch of Wikipedia documents. Okay, so I've ingested Wikipedia, I've ingested Twitter into my own index here inside the Accumulo. Do that query, and then I can ask for nodes that return what's in the neighborhood, so what are the links that are exposed in that document. And all these things fit very naturally into the sqrrl API that we're building. We can also do things like stats queries that go out. Interactive. Here's like a KDB 99 data set that basically a bunch of attacks that were registered and collected for a conference. We do very quick visualizations. We build custom indexes in this space that basically use some of those hierarchical design patterns to just pre-index particular combinations of fields, or do the full lookup, and then use the aggregators and iterators inside the Accumulo to provide server-side aggregation. So it's a very versatile data set, our database, and I hope you guys will give it a try at some point. So we're on a passion project as of about a year ago. We've been on for 30 years. So check us out. We're starting to get quite a bit more participation. In particular, the development community around Accumulo right now is sitting mostly in Department of Defense spaces and intelligence community spaces. So we could probably use your help to actually bring these guys out and into like the real world that we all live in here. So this is great. Ask questions. I'd love to see you guys on the project. Next, I'll take any questions.
Hi. It's very interesting to see the concept. It is really amazing actually. You have multiple data sets with the different varieties of security level needed. It's being the most wanted technology I would see. Most of the DBs and the infrastructure managers who want to do that. So the question back to you is, how do you relate this technology to most related data warehousing or OLTP service areas? So right now, most of the technology that you put at the patterns and everything, that's revolving around the p-value pair most of the times. So I'm not seeing immediate benefit to implement the real-time technology other than HPs or Cassandra or any other p-value pair based on databases. Do you have any answer for that?
Well, the reason that we're doing this from the start is the p-value pair paradigm here really gives us a lot of flexibility. I've shown quite a breadth of the range of what we do. I think there is a lot of research to do in terms of like the right access methods for that. But at the same time, with this key value paradigm at the core, we can throw in the cell security that you're finding great access to it. So that's sort of
short up, yes.
Okay.
But I think we need a little bit more description.
So you put a lot of effort in your inverted indexes, which is very important. So why didn't you start with solid and modify that? Particularly to help you out with your search and of course with the index handling and the version and all that stuff.
Yeah, so we actually are using a lot of the routine code to do the solar. Yeah, so why did we start with Solo? Why did we start with Solo's great at what it does. I think that one of the big drivers that led us towards more of a table model is having scalability to upwards of thousands of nodes with low administrative overhead. Are you suggesting that Solo is also? So, it just seemed like the right model to use. And it was flexible for using a whole bunch of different design patterns as well. It's not just the information retrieval type paradigm that we're going after. I'd like to see a lot more collaboration with Solar as well.
Sorry, this is a dumb question. Why another database just or another platform just like HP is similar to it, so what is the idea?
Yeah, so some of that, we have to talk about the history here, right? Which is 4 years ago we started developing Accumulo. And at the time, there were a number of contenders in the space, and a lot of them were very early in the maturity space. So it wasn't obvious which one we would pick to sort of group with. There's also a lot of government policy that plays into this, unfortunately. So government playing in open source has started to get more popular these days, but at the time it was difficult for us to participate. If we were to start now, I think we would look at HPS and potentially try to build off that. But 4 years ago, that didn't make sense.
So if you're not in government, what are the reasons to choose your product over Israel?
Well, so one is cellular security, right? He offers that cellular security. I don't think really anybody else offers that type of capability. There are a bunch of people still using this in government, right? So that's just growing. There's a huge user community. If you look at the big blob that you see around the DC area, that's indicative that that's really where the user community is there. So the government and the Department of Defense and the contracting base around there is extremely well funded. It's a very large source of talent. A lot of that is going into this kind of project. So it does have a big community supporting it, and it's got some features that really not such.
KRS mostly. I have done MSA projects in terms of assets that you're talking about, what about audio, video, animation assets, which should be very much important to the agency for them to, database and query, etc. And also identify the hacker profile. What are the features that you can do in Accumulo?
Sorry, I missed the last part of that.
How would you be able to identify and profile a potential hacker?
How would you use this for something like?
Identify.
Yeah, and that's a huge discussion because there are a whole bunch of ways you can do this. but people use this by looking at streaming type sensors where you've got data flowing in at higher rates and they sense it quickly. There's a lot of aggregation techniques that fit with this. In terms of like other types of data, we might have images or building on top of these like inverted indexing techniques is like you do